Well, hello everyone. Let's get started with another lesson in chemistry today. We are going to study lesson 13, hybridization. So if you'll get out your study guides, let's get started. Lesson 13, hybridization. Essentially, hybridization is more of an advanced topic that expands our ideas of the valence bond theory. Remember, in the valence bond theory, is that when a covalent bond is formed between two atoms, that the orbitals of those atoms will overlap to form that covalent bond. And we can have two types of orbital overlapping. We can either have head-to-head overlapping of orbitals, which is a sigma bond, or we can have two p orbitals, two of them, that are side by side, parallel to one another, that overlap side by side. And that's called a pi bond. And only p orbitals, you got to remember, only p orbitals can do side by side bonding. Okay. And then we also talked about that the difference between a single, double, and a triple bond. So in a single bond, you can only have a sigma bond, a head-to-head overlapping. Okay, so every single bond is a sigma bond. In a double bond, you have a sigma and a pi bond. And in a triple bond, you have a sigma, pi, and pi bond. Okay, and so we will look at this a little bit more with the involvement of what is known as the hybridization theory of bonding. Okay, so let's go right into hybridization. To understand what we mean by hybridization, we need to talk about hybrid orbitals and the process of hybridization. So essentially, hybridization occurs when you take standard s, p, and d orbitals and you're going to combine them together. And as a result, you're going to form some brand new orbitals that are called hybrid orbitals. And these hybrid orbitals are going to occur around a central atom in a molecule. Okay, and that's important. So what we can kind of generally think about this is that you take your standard P, you take your standard S, and you mix them together, and they form these brand new kind of combined orbitals. And the reason why we call them hybrids is because they are a mixture of both the S and the P together. So they're hybrid. They have characteristic of S and P. All right. Now, in this lesson, we are only going to focus on S and P orbitals hybridizing and not D orbitals. There is been some recent developments that D orbitals may not really hybridize. And so both the AP and IB exam will no longer test on D orbital hybridization, right? So again, all we're going to look at is an S orbital and then the P orbitals combining together, mixing, creating a brand new set of orbitals that are called hybrids or hybrid orbitals. And it is also really important to understand that only the central atom matters here. Only the central atom in a molecule, in a bonding situation, is going to hybridize. All other atoms will not hybridize, only the central, okay? All right, let's talk about our first set of hybrid orbitals. These are known as sp3 hybrid orbitals, okay? The reason why we call them sp3 is because they are a mixture of one s orbital, one standard s orbital, and three standard p orbitals. So you take your three p orbitals, your one s orbital, and you mix all of them together, and as a result or an outcome, you're going to form a new set of orbitals that are known as sp3 hybrid orbitals, okay? So why does this occur in the first place? Why do these orbitals mix together to create these hybrids? Why is that important, and why is that such a big deal? Well, let's take a look at carbon. Carbon is often a essential atom in many, 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 many molecules, okay? So carbon is a classic example of an element that will go under hybridization. In fact, I should tell you that hybridization is limited to only a few common atoms like carbon, nitrogen, oxygen, okay? Very limited. However, carbon, nitrogen, and oxygen dominate molecules. So most molecules contain hydrogen or contain carbon, nitrogen, and oxygen. Okay. So let's focus on carbon for right now. All right. So carbon, we're going to draw an orbital diagram of your basic, normal, everyday carbon atom. Okay. So it has a 1s subshell, right? And that 1s subshell is going to be full. And then it's got a 2s subshell. And that 2s subshell is also full, okay? And then we go to the p subshells, the p subshell, the 2p. And for carbon, it has one electron in one of those p subshells and another one in another p orbital, okay? So in other words, we have in the 2p subshell, we have two orbitals, 2p orbitals that are half full, and the other p orbital is empty, okay? Now, if you think about the valence bond theory, in order to form a bond, we have to form an overlap of atomic orbitals. Well, if this is the case, we could essentially form an overlap of one p orbital here and another p orbital here with the other elements. So what that means is that the way this is written currently is that carbon only can form two bonds. It can form a bond here and a bond here, okay? But that's it. Well, that's very limiting to carbon, when in fact, carbon can form more than two bonds. It can form two bonds, it can form three bonds, and it can form even four bonds. Fact is, it is most common of forming four bonds, all right? Well, if orbitals have to overlap in order to form this bonding, then how in the heck can we form four bonds? Well, the only explanation is that the carbon atom has to undergo hybridization, all right? So in this case, we're going to show you how carbon undergoes hybridization to form sp3 hybrid orbitals. And in the result, this will allow carbon to actually form four bonds, okay? So this is what we're going to do. We're going to draw an arrow, and we're going to go through hybridization. By the way, I want to mention one thing. You already know this, but to remind you, the energy, excuse me, is increasing, right? As we go up, right? So just keep that in mind for just a moment, okay? Now what we're going to do is to form these hybrid orbitals, we are going to take our 2s, and we're going to take all of these 2p orbitals, and we're going to mix them together. And as a result, you still have your 1s subshell, which is full. And then you create four, yes, four hybrid orbitals that are known as sp3, okay? All four of these are specialized sp3 hybrid orbitals, okay? Again, we call them sp3 because it's this mixture of one s orbital and three p orbitals, okay? Now, because we mixed four orbitals, an s, and 3 p's, we get 4 hybrid orbitals out, okay? So the number of orbitals that you mix is equal to the number of hybrid orbitals that you make. That's important. So again, I mix 4 orbitals, I get 4 hybrid orbitals out, okay? So these hybrid orbitals are actually lower in energy than the 2p. Now, they are higher in energy than the 2s, but nevertheless, they are lower in energy than the 2p. And every hybrid orbital of these sp3 hybrid orbitals are equal in energy, which is why they're on the same level. Right now, this is the second energy level, so we're going to call this the 2 sp3 hybrid orbitals. Sorry. Now, these 4 electrons then in the valence shell are now going to be placed in each one of these hybrid orbitals following Hund's rule. So you have 1 there, 1 there, and 1 there, and finally 1 there. So those are 4 electrons that originated from the 2s and the 2p. Now, look what happened when we made those hybrid orbitals. We now have 4 possible overlaps that can occur. We can create a bond here. We could create an overlap here, an overlap here, or an overlap here. So therefore, we can create 4 bonds with the carbon atom, okay? So with sp3 hybridization, it will result in 4 single bonds. Therefore, we can form with sp3 hybridization 4 sigma bonds, and that's really important to remember. So with sp3 hybridization, we can form 4 sigma bonds. So we have head-to-head overlapping that will occur in these sp3 hybrid orbitals, okay? So that is known as the sp3 hybrid orbitals. But let's look at some other ones. Oh, before we do that, I want to show you one thing. So this diagram represents kind of what we just went through, except what you'll notice is that the 2s, original 2s, is missing an electron. And that is because before hybridization really occurs, the electron that was here is actually going to become excited and is going to be promoted up into the 2p orbital, okay? Now, once this electron is up in that 2p hybrid orbital, now all 4 of those can now combine and hybridize into the 4 sp3 orbitals, okay, which are depicted right here. And notice that we can form these 4 overlaps in this regards. Now, this also shows you kind of what the each sp3 hybrid orbitals look like. You get a very large lobe with a high electron density and a very small lobe with a low electron density. And the reason why for this shape is because it is a mixture of the p orbitals and the s orbitals. And so you get this really large lobe and a small lobe, okay? And where the large lobe is, of course, has the greatest electron density. So that means it has the greatest probability of finding a bonding electron or a pair of bonding electrons in this lobe. So somewhere here and here, we're going to have a bonding, and a bonding situation occurs. So one donated from one carbon, and then the other electron donated from some other atom that is bonding to, okay? So I just wanted to show you that really quick. All right, let's go into the next type of hybrid orbitals. These are known as sp2 hybrid orbitals, okay? Now, sp2 hybridization occurs because we take one s orbital and only two p orbitals, and we combine them together, okay, to form these new hybrid orbitals. So let's go back to our carbon example again. So we have the 1s, which is full. We have the 2s, which is full. And then we have our p's. 1, 2, and 3. There's our 2 p's. And again, for carbon, it's going to have a electron there and there. Okay. Now, if they're going to go under hybridization, we're going to just now take the 2s and one of the p orbitals and this p orbital, and we're only going to combine these, essentially these three together. Okay. So as a result, we still have our 1s orbital. Okay, that's our core electrons. But now we have, oops, lights off. Now we have our new hybrid orbitals. Now, how many hybrid orbitals do you think we're going to get? If you said 3, you're right, because we mixed 3 orbitals together, right? So I mixed an s and 2 p orbitals, excuse me. And as a result, 3 orbitals mixed, we make 3 hybrid orbitals. So, and those 3 hybrid orbitals are going to be lower in energy. sp2. And we're going to have an electron in each one of those. All right. Now, wait a minute. You're going to say, well, hold on here. What happened to the other electron? Okay. Well, this electron is going to get promoted, excited to that energy level, or to that p orbital. Okay. But we're not going to mix this p orbital. So what really is happening here is we have a 2p orbital still left over with an electron in it. Okay. So we are forming only 3 sp2 orbitals, 3 of them, because we're only mixing 2 of the p's and 1 of the s's. We still have a p orbital left over. And so that's going to have an electron in there. Okay. So what's interesting about this, though, is that we can still make 4 bonds, right? 1, 2, 3, 4. However, we're going to make a little bit different bonds. So with the sp2 hybrid orbitals, we can form a head-to-head overlap in each one. And so with these sp2 orbitals, sp2 hybrid orbitals, we can actually form 3 sigma bonds. But with the 2p orbital that's left over, we can actually form, so with that p orbital left over, we can form 1 pi bond. All right. So with sp2 hybridization, we often form 3 sigma bonds and 1 pi bond as a result. Okay, and remember, a pi bond is going to occur with a p orbital, which we have, and another p orbital that overlaps side by side. Okay, so this is a way in which we can actually start creating not only single bonds, but we can also get double bonds when we do sp2 hybridization. Okay. All right. All right, now this is going to quickly show the representation of what we just went through, where we have taken that 1 electron that was here, and we've already promoted up to a p orbital. And what we're going to do then is combine all of this together. We're going to mix these orbitals together. And by mixing them, then we form our 3 sp2 hybrid orbitals. And then we still have our 1 p orbital left over, okay? And so these right here can form our sigma bonds. And now this leftover p orbital is available to form a pi bond, okay? Which of course pi bonding is found when we create a double bond, right? Because a pi bond, or remember, a double bond is made up of 1 sigma and 1 pi. And so we can actually combine one of these sp2 hybrid orbitals and the p orbital, and that could be our double bond that we make out of that. Okay. All right, now we're going to talk about one more type of orbital or hybrid orbital, and that's sp. Okay, so just as the name applies, we're going to take one s orbital and only one of the p orbitals and mix them together. Okay, so let's draw our diagram of what this would look like for carbon again. So carbon has a 1s orbital that's filled. Its 2s is filled, right? And then its 2p has two half-filled p orbitals and one empty one, okay? We know this. Now, all we're gonna do is create now a hybridization by combining the s orbital, the 2s, and one of the 2p's together. And as an outcome, we get how many sp orbitals? 2. That's correct, because we're combining only 2 orbitals. We're combining one s and one p, and therefore we get 2 orbitals out of it. Okay, so we still have, by the way, our 1s, so I'll still draw that, still filled. That's our core electrons. And then our valence electrons are now going to be in an sp hybrid orbital. We have 2 of them. And what's left over is 2 p orbitals, okay? And so we have an electron here and an electron here. And then we have an electron in one of the p orbitals and another one there, okay? And so this is the result of sp hybridization. 2 hybrid orbitals are made, and we have 2 p orbitals left over, okay? And by the way, this is going to be 2 sp, right? Because it's in the second energy level, right? So we can still form 4 bonds, right? 4 bonds, but the bonds are going to be a little different. With the hybrid orbitals, we can still form head-to-head overlap or sigma bonding. So with the erase that, start again there. So with the sp hybrid orbitals, we can actually form 2 sigma bonds. But with the 2 p orbitals, with the p orbitals left over, we can actually form 2 pi bonds. All right. So where do we find 2 pi bonds occurring? Well, triple bond, right? So with sp hybridization, you often get triple bonding occurring, where you get your sigma, right, the head-to-head overlapping, and that can take place with one of the sp orbitals, and then you get side-by-side overlapping, a p orbital, and then another p orbital, right? Sigma, pi, pi. And that's where we use these orbitals to create overlapping to form single, double, and triple bonding. Now, again, this is only going to occur around the central atom. So all our examples so far have been essentially using carbon. And I use carbon because it's going to be the most common, the one that we see most often. But we could apply the same principles to other central atoms in other molecules, okay? And we'll give you some examples here in a moment, but we're going to show you a fast, short way to determine hybridization really quick, okay? Okay, and just as before, the forming these 2 sp hybrid orbitals, we are going to take and essentially have 2 p orbitals excuse me, man, I'm sneezing. All right, something is in the air in this room. All right, 2 p orbitals that are not going to combine, and then our 2 orbitals that are combining right here, okay? Oh, geez, so sorry. So those 2 orbitals are going to form our 2 sp orbitals that we talked about. So again, these orbitals here, these sp orbitals, can form our sigma bonds, and these two p orbitals can form our pi bonds. Okay. All right. So we kind of just talked about this, but let's again summarize it all into one idea. All right. So with sp3, with sp3 hybridization, sp3, we can only get sigma bonding occurring. So we can make 4 sigma bonds, all right, as long as carbon is your central atom. Now, with sp2 hybridization, we can combine the 3 sp2 hybrid orbitals together. Here's carbon, and that's what these are depicted here in red, is our sp2 hybrid orbitals. So this one right here is an sp2 hybrid orbital. This one is an sp2, and that is sp2. Okay, but then we have our 1p orbital left over. This is our p orbital. Okay, so all of these sp2 hybrid orbitals that you see, these 3, can form sigma bonds only. Okay, they can only form sigma. But this p orbital can be involved in forming 1 pi bond. Okay, just as kind of we've talked about earlier. And then with sp hybrid orbitals, when we combine them together in our structure, here's our carbon. We have a sp orbital right here. We have another sp orbital right here. Those are our 2 sp orbitals. And then we have our 2 p orbitals left over, right? One here, and that's kind of up and down along the y-axis. And then you have another p orbital that's actually on the z-axis, right? Because that's where we can get our pi and pi bonding occurring, pi and pi bonding, right? And then on the x-axis is where we can get our essentially our sigma bond that can occur. So like right here, that can form our sigma bond, and then so sigma, and then the other p orbital can form pi, and then the other p orbital along the z-axis can form the other pi bond, and that will form a triple bond with our carbon bonding scheme here. Okay. So we're going to use ethane as an example here, okay? So what we're going to form is 2, or essentially a double bond between 2 carbon atoms to form ethane, okay? And so because we're going to form this double bond, we must have an opportunity to be able to form not only a sigma bond, but also 1 pi bond, right? Because we know that this right here must contain 1 sigma and 1 pi, right? And that is always going to occur for a double bond. All right. Now, so what is the type of hybridization that's going to be occurring here, right? So let me kind of show you a really trick to do this really quick to find the hybridization, and then we'll go into more details with ethane, okay? So if you take your central atom, and in this case, our central atom is going to be we have 2 different carbon central atoms, right? But let's only focus on this one here. We'll call this A, and this other central atom we'll call B. So we're going to only focus on A right now. So the way to find hybridization, this little trick that I came up with, okay? What you're going to do is you're going to start with one of the bonds, okay? And you're going to count the domains, okay? So only the domains. and around the central atom, okay? So there's one domain, two domains, three domains, right? So 1, 2, and 3, okay? Now, what you're going to do is each domain is going to represent one of the standard orbitals in the hybridization process. So we're going to start with this first one, and we're going to say this is S, and then you're going to go P1, P2, S, P1, P2. So since I ended on P2, my hybridization around this central atom is sp2. Okay, so when we show you again, you start with S always. So just choose one of the domains and go sp2. So sp1, sp2. Since I ended on sp2, the hybridization around this entire central atom is sp2. Now, I can also do this for the other central atom for B. All right, I start with this one here. I got three domains. So I got S, P1, P2. Again, S, P1, P2. That means this central atom also has sp2 hybridization. Okay. Therefore, if we're going through sp2 hybridization, we form three sp2 hybrid orbitals, and we have one p orbital left over. So we have an electron here, 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 and one here. As a result, the three sp2 hybrid orbitals can result in sigma bonds, and the p orbital can result in a pi bond. Okay, so this is where our pi bond is going to come into place. Okay, so now let me erase all this, go back to our ethane structure. All right, so that means what's going on here is the bond, the covalent bond between this carbon and this hydrogen is forming by a sigma bond. It's a single bond. This is forming a sigma bond, and that sigma bond is going to be an S, as we see down here, an sp2, and overlap with a 1s orbital. And the 1s orbital is from hydrogen, and that 1s orbital is going to overlap with the 2s, or the sp2 hybrid orbital of this central carbon atom. And that's going to form a shared pair of electrons in that overlap. Okay, and that's going to happen with this one as well. It's going to form a sigma bond, and we have an sp2 hybrid orbital with an overlap of a 1s. Okay, here's the 1s, and we're going to form a bond between these two electrons, one from hydrogen, one that's in the sp2 hybrid orbital. And we can do that all the way around, right? So this is an sp2, and this is a 1s orbital from hydrogen. This is an sp2, and this is a 1s hybrid orbital. Okay, just like so. And so all of these then are going to be sigma bonds. Okay, so we essentially so far have 4 sigma bonds. And you can always remember, it's really simple. Every single bond is a sigma bond. Okay, it has to be head-to-head overlapping. So let's go to our middle then, between the two carbons, our double bond. Well, our double bond is going to be created in such a way where we have a sp2 and another sp2 that overlap to form another sigma bond. That's the sigma bond part of our double bond. And then we need to form our pi bond. Well, we have a p orbital here and another p orbital on the other carbon atom. And these two p orbitals overlap to form a side-by-side overlapping to share these two electrons. So if I overlay this then this is what I get, is this structure here. And this is my overall bonding structure that shows where my pi bond is and where my sigma bond is. And these are the 4 electrons being shared between the 2 carbon atoms. 1 in a pi bond, which are in p orbitals, and 1 sigma bond, which are in sp2 hybrid orbitals. The sp2 hybrid orbitals are overlapping, okay? Let me show you a 3-dimensional model of this, okay? See if you can see this, all right? So this is what we were just looking at. These right here, these balls in white are my 1s orbitals from hydrogen. So all of these are the 1s orbitals of hydrogen. And it's going to overlap with an sp2 hybrid orbital from the carbon. So that's what's in red. All the red, these are sp2. So sp2 overlap with the 1s all the way around. Our pi bond is right here. Well, first of all, we have our hybrid orbital right here. These are 2 hybrid orbitals in the middle, forming a sigma bond here. And then we have our pi bond, which is formed by these 2 p orbitals. So this is a p orbital, and this is another p orbital. And this like little connector thing is showing the side-by-side overlap of these 2 p orbitals, creating the pi bond that's occurring in this bonding situation, okay? I know it's a lot to take in, but spend some time going back and thinking about this, okay? So again, we have our sp2 hybrid orbital overlapping with a 1s, okay? And then we can see that all the way around this structure where we have hydrogen overlapping with an sp2 hybrid orbital from carbon. And then our double bond is found in the middle, right? These 2. One is a sigma bond, where we have the overlapping of 2 sp2 hybrid orbitals, one from each of the carbons. And then our pi bond is formed by the p orbital here and the other p orbital here that are parallel, that are on the y-axis, and are forming this overlap here. You can also see the bottom overlap, which is represented by this, and that will help to create our pi bond, okay? All right. Whew, I know, it's a lot. All right, let's look at one other structure. Let me draw this structure out. So we're gonna create ethylene, which is acetylene. So it's going to create a triple bond, and a bond there and a bond here, okay? So essentially this carbon and this hydrogen are going to be forming a single bond, and this carbon and this hydrogen form a single bond. But these 2 carbons in the center are going to form a triple bond, right? So first of all, we need to determine what is the hybridization that is occurring here. So we can use that counting method that I showed you. So the triple bond counts as 1 domain, and then a single bond counts as 1 domain. So the hybridization around this central atom, there's our A central atom, here's our B central atom, 2 central atoms, okay? By the way, this is a linear molecule, right? It's a linear. So what we're going to do is we're going to count. So this is going to start with our hydrogen between that domain, hydrogen carbon is going to be S. And then we go to our triple bond is another domain, and that's going to be P1. So S, P1, S, P1. So that tells us that the hybridization around that central atom is just SP. And the same thing with the other central atom, S, P1, SP, okay? So we just count SP, SP, okay? So we know the hybridization that is occurring is going to create only 2 SP hybrid orbitals, and 2 p orbitals are left over, and each one has an electron in it. Okay, so that means that we can form a sigma bond here and a sigma bond here, and then we can form 2 pi bonds. And we need to form 2 pi bonds to create our triple bond, right? So this is for both carbons. Okay, so this is the hybridization that is occurring between both central carbon atoms, right? So what we can do is form a overlap here with hydrogen. So we have the 1s here, okay, and it forms an overlap there. So that's 1 sigma bond from 1 hydrogen, okay, and then we can form. This is going to be a carbon, so this is going to be essentially a sp. We're going to form our center, and that's going to be represented by one of these. And that's going to be another sigma bond that's going to occur. And then our 2 pi bonds are going to be the other part of our triple bond. Okay, and that's kind of what I was trying to get at and show. Oops, cleared the whole thing. Let me rewrite that. So our triple bond, our hydrogen. Okay, so basically for the AP test, this is what you would need to know. You would need to know, one, what is the hybridization around a particular central atom? So if they want to know what's the hybridization around central atom A, we would just say it's sp, hybridization. And then they would want to know, like, okay, how many pi and sigma bonds are occurring? Well, you have a sigma bond there, okay? And you have a sigma bond there. So far 2 sigma bonds. And then in our triple bond, we have a sigma bond. So we have another sigma bond, right? And then with our triple bond, we have sigma, pi, and pi. So we have right here with these two, we have our 2 pi bonds. Okay, so we would say that overall this molecule has 3 sigma bonds and 2 pi bonds. Okay, and you would need to know that for the AP test. The hybridization, sp, and the number of sigma and pi bonding. And then you would also need to know the shape of the molecule, and you would also need to know the polarity of the molecule. Is the molecule polar or nonpolar? In this case, it's going to be nonpolar. And is the what's the shape and the Vesper shape? And of course, that would be linear in this case. Okay, so those are the things you would need to know. Okay, so let's say show you a model of what we just did. This is the triple bond that we looked at. Okay, so here is the hybridization, sp hybridization, overlap with a 1s orbital from hydrogen. Here's the other one, the 1s and the overlap that occurs with the essentially sp orbital. And then we have our triple bond in the center. So we have our p orbitals here. They're going to form the pi bonds. Here are 2 p orbitals that are along the, again, y-axis. And then we have a z one now. We have a p orbital here on the z and a p orbital here on the z. So therefore, we have another pi bond that occurs with this side-by-side overlapping. So we have overlapping here and we have overlapping here. Okay, so that's our 2 pi bonds that are occurring. And right in the center here is our sigma bond between the 2 carbon atoms. And these would be the sp hybrid orbital overlapping that's occurring in the center right here. Okay, so this is the model of what is on our screen currently for that Lewis structure. Okay, off of that. Boy, I hope this is making sense to everyone. I know it's a lot. Okay, so what I want to do right now is summarize most everything we've done here. Okay, what would be expected on the AP exam or IB exam? Okay, so the first thing, if they give you a molecule, they would expect you to be able to draw the Lewis structure for it. So I'm going to quickly draw the Lewis structure for water, and I'm going to draw it in such a way that shows its correct geometrical shape in that bent structure. Okay, we have 2 lone pairs here. Okay, so this is our structure. It has a 105-degree bond angle, right? 105. It is a bent structure, so they would want to know that. And they would also want to know the polarity. And we know that water is polar, so we would say that it's a polar molecule. All right. They may even want to know where the positive and negative charges are, as far as the partial negative charge up here by oxygen, and the hydrogens down here are partially positive. Okay. They'll want to know where the dipole is. All right. So essentially, the overall dipole is going to be straight up, right? Where it's pointing to the most electronegative atom. So partially negative and partially positive down here. So we got our dipole. We know it's polar. We know the shape. But now they're going to want to know, what is the hybridization around the central atom? Well, the central atom is oxygen, right? So we're going to use our little trick that I showed you. And all you need to do is count the domains, okay? There goes our light again. All right, so we're going to count our domains, okay? So each domain includes a bonding pair and a lone pair, okay? So we actually have, if we count the domains, 1, 2, 3, and 4. We have 4 domains. So the way we're going to do this is we're going to count, we'll start right here, and we'll go S, and then P1, P2, and P3. We ended at SP3. So that tells us that the hybridization around oxygen is SP3. Okay, we have SP3 hybridization. All right, so let's do that again. We can show you S, P1, P2, and P3. SP3 hybridization. And that's all you need to be able to do. Use that little trick and you're good to go. All right, so we know what the hybridization is. We know it's polar. We know the shape. We know the dipole, where that's at. What about the number of pi and sigma bonds? Well, we know that each single bond is a sigma bond. We have 2 single bonds, so we have 2 sigma bonds. And the lone pairs don't matter, okay? There's no bonding going on with those lone pairs. So we only have 2 sigma bonds, and we have no pi bonds in water, okay? So that's kind of essentially what you would have to do for the AP or IB exam here. All right, let's do carbon dioxide really quick. So I'll draw the Lewis structure. Carbon dioxide has a double bond there, another double bond there, has a couple lone pairs on the oxygen, like so, but no lone pairs on the carbon, okay? So first of all, what's the shape? Linear. The angle, 180 degrees. Is it polar or nonpolar? Well, it's going to be nonpolar. Carbon dioxide is nonpolar, right? All right, now what about the hybridization? Well, let's use our trick. So we have 2 domains around the central atom, which is carbon. All right, so we're going to go SP. So the hybridization is SP. So we can assume that we know that that carbon, that central, is an SP hybridization orbitals that are going to be formed. Okay, so how many pi and sigma bonds are there? Well, we have 2 double bonds. Each double bond is going to have 1 sigma, right? So we're going to have 2 sigma bonds, and each double bond is going to have a pi bond. So we're going to have 2 pi bonds. Okay, remember that a double bond is a sigma pi. So we have sigma pi, and we have 2 of those, two double bonds. So therefore 2 sigmas and 2 pi's. And that's all there is to it, okay? All right, let's do one more. All right, we're gonna do the carbonate ion here. Now the carbonate ion is gonna have a Lewis structure that looks like this, right? And it has some lone pairs, right? More lone pairs. And more lone pairs. All right, now this is an ion, so I need to put brackets around it because it is an ion. It's going to have a -2 charge up here because of its ion. Now, really, this carbonate ion forms resonance structures. So if it can form resonance structures, we would need to indicate that. So we're going to show another double bond there, another one there, and there. And then we're going to put our 2 negative. Okay, there's lone pairs, right? Bum, 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 bum. Lone pairs, lone pairs, lone pairs, lone pairs, and more lone pairs. Okay, and then one more resonance structure that we can draw here. Put the double bond here, single bonds, and terrible bracket. Let me see if I can do a better bracket here. Okay, well, like so. Okay, so there's our 3 resonance structures. All right, so all 3 have the same shape. So what would the shape be? It would be a planar structure, a trigonal planar. And the polarity, well, it would be non-polar. Okay, so all of these dipoles cancel out. And you can go back and verify that, but essentially carbonate ion is nonpolar and is a trigonal planar structure with 120-degree bond angles, okay? But let's focus on the pi bonding, sigma bonding, and hybridization. So since they're all the same connectivity, they're gonna, or the same skeletal structure essentially, they're gonna have the same hybridization and the same number of pi and sigma bonding. So we only have to use one, okay? So we're gonna use our little trick. We have 3 domains around the central atom, right? 3 domains, 1, 2, and 3. So we're gonna go S, P1, P2. So that tells us that we have S, P2 hybridization, okay? And that should make sense because we do have a double bond. Remember, we create sp2 hybridization with double bonds, okay? So sp2 hybridization. Now, how many pi bonds or sigma bonds? We'll do sigma bonds. We have 1, 2, 3. So we have 3 sigma bonds here, and the double bond is also going to create 1 pi bond, okay? So we have 3 sigma and 1 pi bond overall. So remember, the double bond is a sigma pi, okay? So those are 3 examples of possible ideas that you would have to do on the AP or IB exam. Again, draw the Lewis structure, determine the shape and bond angles, determine if it's polar or non-polar, draw the resonance structures of the most stable structure, right? And then determine the hybridization around the central atom that they want you to. And then determine the total number of pi and sigma bonds. And voila, you're done. And that's all there is to it. All right. So we're going to end with this lesson here. So yeah, until next time, study hard, and we'll see you later.